Why to know posterior? In our lectures on classification, you would have looked at one particular thing. That is, you would have noticed that we always discuss about posterior, the importance of posterior. That is P of Ck given X. Why is it that we are giving so much emphasis on posterior? So this lecture is about why should you know posterior? What is the importance of knowing posterior as a designer of a model? That is, if you can simply design a model like this, right? As we told, the simplest approach was if your input is X, your model will make a, let's say, function f of X, which will classify it into C1 or C2. So this is a very simple classification model. Why should you go and see what is the posterior and work accordingly? Why should you generate posterior as your inference problem and then use your decision theory to make final classes C1 and C2? What is the importance of knowing posterior? That is what this lecture is about. So the first thing, what is posterior and why it is special? Let us start with that. So it combines the prior knowledge with the observed data. That is, how do you find posterior? P of Ck given X, where X is your input data, Ck is the class. So this is P of X given Ck into P of Ck divided by P of X, right? So what this does is two important matters. One is that it has prior. What is prior? Prior depends on your subject knowledge, or maybe you are deriving it from the data. But either case, the point is before you see the data, you are making a approximation of what can be the probability for C1 and what can be the probability of C2 according to your knowledge before seeing the data X. That is what prior is. So how this helps is, in case, let's say the data is a bit imbalanced. In that case, your prior can really come helpful, because your prior can tell that, see, I already know that the chances of class C1 is this much, or already I know that the chances of class C2 is this much. So accordingly, it can balance out the imbalances in the actual data. And the same way, in case you make a slight mistake in choosing the prior, seeing your actual data can also compensate a bit. So this posterior, it brings in these two components, the actual data, observed data X, and the prior P of Ck, which combinedly provides you some positive outputs while you're using it for classification problem. This is what posterior brings you. Now, if you know the posterior, what are the advantages as a designer who is designing the model, or a machine learning engineer who is coming up with a machine learning model? So the first advantage is in dealing with skewed data. What is skewed data? Skewed data is in which data is distributed in the ratio, let's say 1 is to 999. This is what you call as skewed data. What is this? For every one data that is there in C1, your input data that has 999 inputs which are in class C2. So this is very much skewed, because let us say if you designed a basic model in which if you give an input X, it will go into the model. This is your model. Model will design a function f of X which will output classes C1 or C2. Let us say you made this basic model without looking at the posterior. What if the model fools you and it works such that whatever be the input you give, whatever be the X you give, it will always tell you that the output is C2. It is not applying any logic. It learned that for this particular data set, because it is skewed, it will work this way. That is, irrespective of whatever you may give, it will always say C2. What will happen then? The accuracy of this model, if you check, it will be 99.9%. Why is it? Because for every 1000 inputs, model will get 999 correct, because in your data, 999 belongs to C2. So in this case, accuracy wise, this model looks really good. 99.9% accuracy for a classification model is extremely good. But is this right? No, it is not. Because when you are designing a model, you want it to apply logic in order to understand whether it's C1 or C2. If it's simply to say that it is C2, why should you even have a model? So in these sort of cases, posterior helps you finding a way to weigh different classes appropriately. That is, C1 and C2 can be weighed appropriately, because in case of posterior, you are finding the probabilities of each class. That is, given the value of x, what is the probability of x being in C1? What is the probability of x being in C2? You are finding these two separately. Because of this, you have a better chance of dealing with the skewed data. And the next thing, one thing you can do in order to deal with skewed data is that once you get a skewed data, you can find an artificially balanced data set and find the posterior of that data set. Find P of C1 given X and P of C2 given X for that particular data set, which is artificially balanced. Let's say in that data set, your data is now in the ratio 40:60. Okay, let us say now it is in this ratio. You find the posterior of this data set, and then what you have to do, you have to divide by the ratio in this data set. That is 40:60 is the ratio here. So by that ratio, you have to divide the posteriors that you found, and then you have to multiply it with the ratio of the target data set. That is the actual data set that you have, which is skewed. This way, you have an option of finding the posteriors. But remember, when you are applying these sort of techniques, one thing you have to keep in mind is that finally, when you sum all the posteriors, let's say C1 given X, C2 given X, when you sum it, it should be 1. So for that, you have to normalize. In case the sum doesn't turn out to 1, it will be an issue. So in such cases, when you are doing operations of this kind, make sure that you normalize so that sum is always 1. So this is the first advantage when you're dealing with skewed data in which one class is dominating over the other. In such cases, knowing the posterior will be very helpful. The second advantage. Why should you know the posterior? Second advantage is your reject option. So in our previous lecture, we had seen reject option. What is the reject option? Your model will sometimes say this data belong to class C1. Sometimes it will say this belongs to class C2. And whenever it is in this gray area between C1 and C2, it would say, I don't know which class it is in. So you have to have either human intervention or you won't be able to determine the class. So what is the advantage of reject option? This is implemented so that you can minimize the misclassification rate, because in this gray area, your model is actually not very sure. So knowing the posterior helps you here. How does it help you? Let's say you simply made a normal model, the very basic model in which x is the input. Your model using the function f of x simply says it is C1 or C2. Let us say your model said it is C1, you marked it as C1, and let us say you were using this for some financial application or something in which you had to invest money in, say, in one company, company 1 and company 2. You are trying to invest in one of the companies. So you put all the factors and decided which company you have to invest in. So because your model said C1, you put all your money, 100% of your money into company C1, thinking you will make better profit from investment in company C1. But let us say the reality is that if you go and check the posteriors, that is probability of C1 given X and probability of C2 given X, if you actually check the posteriors, maybe here it is 0.51, that is 51%, and here it is 0.49. What does this actually mean? This means your model is actually not very clear that C1 is the best option. Instead, your model chose the class C1 just because P of C1 given X was higher value, but it's not so high. It's like comparable values, like 51% and 49% are very comparable values. So what should your model ideally do? Your model should ideally come and tell you that, see, I'm very confused. By very slight difference, I think P of C1 given X is higher, because of which class C1 should be a better option, but I don't know, right? According to me, both are equally probable. In that case, what can you do? You can put 50% of your money into C1 and 50% of your money into C2, because you don't know which one will be successful in future. So in such cases, knowing the posterior helps you decide. That is, you will have a reject option. And how did the reject option work? We had seen in one previous lecture the graph of reject option. If you draw it like this, let's say this is your x, okay, this is your x, and this is 0, this is 1, this is a probability. Let's say P of C1 given x comes like this to 0, and C2 given x goes like this. So P of C1 given x is very high here, C1 given x, and it comes down to 0, and P of C2 given x goes high as the value of x increases. Here, let us say this is your threshold theta. This threshold, according to this threshold, what will your model do? Whenever your value is below this threshold, value of both the probabilities are below this threshold, it will consider this as gray area. So whatever be the value of x in this range, it would say, I don't know what is the class to be selected. What is the importance of posterior here? Because how do you implement the reject option? You implement it by saying that all your posteriors P of ck given x should be greater than or equal to some threshold theta. So without knowing the posterior, implementing the reject option is just not possible. So in order to implement this, you need to know the posterior, right? So that was a second option. Now let us see what is the third option. Okay. Third advantage while we make use of posterior, it is that in case you want to revise elements of the loss matrix. So previously we had seen examples of cases where we implemented loss matrix. So what is the use of loss matrix? Loss matrix, it was something like this, that is C1 and C2, let these be your true classes, that is actually your data belong to C1 or C2, that is true class, whichever it is. And here these C1 and C2s, let this denote the classes that you have assigned. Let us say our classes that we have assigned. So in case the true class and the class that we assign matches, then there is no loss. Then we'll say zero loss. C2 and C2, in these cases, no loss. But there will be some practical applications in which we want to weigh different type of misclassifications differently. That is, if C1, actually it is C1, but it is C2, maybe the let's say our loss is 10. But actually if it is C2 and you misclassified as C1, let's say loss is 100. In this case, loss is higher. So in case you want to make these sort of changes, then it may be so that in such models, with time or with some sort of conditions, these priorities may change. That is, for now, the priority may be that C2 misclassification is of lesser priority than misclassifying C2 into C1. But maybe after some time, maybe it will change to maybe this will become of priority 1 and this will become of priority 100. So if you have this sort of a change in the loss matrix, what issue will you face? How do you use the loss matrix for assigning each particular value of x? The x is the input. What do? You wanted to minimize this one. Sum over all the k. What did we learn? LKJ, which is from the loss matrix kjth element into P of ck given x, right? This is the value we had to minimize for each of the input value x. That is, you had to see that if you put into class ck, then what is the loss it will face. For each of the classes, you had to see that. So once you see this, in case you have not looked at what is the posterior, the problem is whenever you have any change in loss matrix, you have to start from ground zero and prepare the model again. Whatever you did till date, everything is gone in vain. You have to start from ground zero, prepare a fresh model. That is what you will have to do if you don't know the posterior. But in case you know the posterior, you have already found the posterior and you are using the method in which take the posterior and then use decision theory to find the final solution. In that case, if you know the posterior, what can you do? In this equation, you can change the values of loss, that is LKJ value. This you can change and use the posterior that you already found. Using this, you can again simply redo the problem without again going and finding the posterior. So here your work becomes easier in dealing with any changes that would come in the loss matrix. Loss matrix is basically the priority of different sort of misclassification. Okay. What is the fourth advantage? Fourth advantage is in combining models. That is, there will be cases in which the actual task is very complex. Let's say this is your actual task, which is very complex, and you would prefer that you divide it into smaller parts, then first solve this, then solve this, then solve the final one, and then combine all these in order to get your final model, final output. In this sort of cases, you can do this I'm talking only about classification in this lecture. You will be able to do this only when you know posterior. Then it will be easier for you to break the problem in case of such complex problems. How does it happen? I'll explain you. See, what should you be finally able to identify in order to find a let's say large model from the small subcomponents. If you want to make the large model, what do you want to identify finally? The final posterior. That is, let us take an example. Let us take the example which we already took in most of our lectures. That is, if it is the border of your country, you have multiple CCTV cameras. Let's say cameras are looking into who is approaching. If it finds some people who are approaching, what will it do? It will scan them and find certain attributes. And if it is an enemy, what do you have to do? You have to send the troops so as to protect, right? If it is not an enemy, you don't have to send the troops. This is the whole idea. So let us say the features that you are taking, let's say you are only considering dressing and body language for now. I'm taking only two because otherwise our equation will get larger. Let us say the x which is your input includes dressing and body language of the people. These are two components that you identified from the camera. What do you want to finally find out in case you want to build a larger model? That is probability of, what do you have to find out? XB, that which one corresponds to body language, and XD which corresponds to dressing, given CK. Sorry, you have to find the posterior P of CK given XB XD. This is what you have to find. This is the final posterior that you want to find. If you want to find this from the two submodels, first one which only deals with the dressing data, second model which only deals with, let's say, body language data. Let us say this is how you are planning to implement it. Because implementing both together is difficult for you, you decided that you will make a smaller model which deals only with the data about dressing. Then you will classify it. Then you will find another model which only deals with the data of body language. Then you will classify it, and you will use this data together in order to find the final class, whether it is C1 or C2. C1 is, let's say, enemy. C2 means not an enemy, into this final class based on both these submodels. If you want to do this, you should be able to find out this posterior, that is CK given XB and XD. This is what you have to find out. And if you are using the smaller model, the data that you have will be P of CK given XB separately and P of CK given XD separately. This is what you will have in case you are dealing with two smaller models. So what I will try to prove now is that from these two values, you can ultimately find out this value. If that is proven, then you know that from the submodels you can easily make the larger models. So if this is proven, then I can tell you that if you know the posterior of the submodels, you can find the posterior of the larger model. If you know the posterior, then you can do the classification, right? So this is what we'll prove now. I'll show you. So there are two inputs, XB and XD, and what you finally want to do is posterior P of CK given XB XD, right? So the first thing, let us take P of XB X. This is class conditional density given CK. What is the speciality of this? Here we are considering that XB and XD, that is data belonging to body language and data belonging to dressing, these are independent. That is, you independently observe the data belonging to body language and that belonging to dressing. So these are not interrelated. So whenever two events are independent, let's say any two events A and B are independent, what is the condition? P of A, B can be written as P of A into P of B. This we have learned in a probability lectures. That is, whenever two events A and B are independent, P of A, B equal to P of A into P of B. That is, probability of A and B occurring together is same as the multiplication of that is the product of probability of A and probability of B. So the same logic if you apply here, this will become P of XB given CK, right, into P of XD given CK. This is fine. So for now we found that finally we have to see whatever it is corresponding to the posterior. So with class conditional densities XB, XD given CK, we found that because XB and XD are independent, we can write it as P of XB given CK into P of XD given CK. Next step, in the next step, let us try to find the posterior, that is P of CK given XB XD. This is a posterior. This we know is directly proportional to, that is from base theorem knowledge, we know that this is directly proportional to P of XB XD given CK into P of CK. You agree with this? XB XD given CK into P of CK. Now this you can substitute with this term because both are independent, right? So I'm going to substitute with this the independent terms. P of XB given CK into P of XD given CK into P of CK, right? This much is clear, right? You are clear with this. What do we have to finally find? We have to finally say that P of CK given XB XD is directly proportional to P of CK given XB into P of CK given XD. Now, P of CK given XB, CK given XB, this we should be able to write as P of XB given CK, that is, this should be directly proportional to XB given CK into P of CK. This is right. This is again from base theorem. You know that P of CK given XB should be directly proportional to P of XB given CK into P of CK. This is, I am taking base theorem's numerator. That's why I am putting directly proportional sign instead of equal to. So in order to match up with this, what I'll do, I'll add an extra CK here. So I'll totally divide this by P of CK and add another P of CK, right? I'll add like this. Here I'll add a P of CK, then P of XD given CK, and finally one more P of CK. Okay. So why did I do this? So that I can apply this rule. What will I do? I'll take this particular term, I'll change it to P of CK given XB, right? And this particular term, I'll change it to P of CK given XD. So I'm going to substitute this term here, that is whatever we found here, that I'm going to substitute here, P of CK given XB, P of CK given XB. And here what can I substitute? Instead of this term, I can substitute P of CK given XD. That is, here I am only looking at proportionality. P of CK given XD. So what does this finally give you? P of CK given XB and XD is directly proportional to P of CK given XB into P of CK given XD, which means if you find the posterior separately, you can combine it up and find the posterior of the whole term, which means simply if you know the posteriors, then it's easier for you to combine the submodels and make the larger model. So these are the major advantages of having posterior. Moreover, you should also remember that posterior also works as regularization. In case of regularization, we had seen that it avoids overfitting with the training data. So how does posterior effect work as regularization? Because because posterior has this term prior p of ck in it, the prior term. Because of that, it won't overfit the with the data x. That is what the input data x, it won't overfit because you are adding a prior. And see, the whole importance of prior is, if you already know that there is some bias, then you can give a slight importance to the other class initially itself, because prior is in your hands, it is in your subject knowledge. Okay.